and we'll have some time at the end. And also, if you're interested in a follow-up discussion, there'll be one this afternoon at 3 p.m. Using the same link that you used for the colloquium. So with that, I will turn it over to Andrei.
Thank you, Dave. Please do feel free to ask questions. It feels a little better with the Zoom setup. If I can answer some questions even during the talk, so I would know that you follow a little better what I'm talking about. So I will just would like to start to remind you that for many years we saw beautiful movies, theoretical simulations of neutron star mergers, and how they would produce, how the two stars would dance around each other, then merge, produce gravitational waves, also produce a cloud of radioactive material that can emit optical light, synthesize heavy elements. And also for many years it was speculated that these kind of events would produce gamma ray bursts, short gamma ray bursts. And 3 years ago, there was a first neutron star merger detected, where all these components were actually observed, both gravitational waves and gamma ray bursts. So this is the gamma ray burst and the gravitational wave picture that I'm sure you've seen before. So the bottom panel is the chirping gravitational wave signal. Our frequency goes up with time. And the three panels above it are the light curves of the gamma ray burst that accompanied that event in 3 channels, between 10 and 50 keV, 50 and 300 keV, and you see about 100 keV integral data. And so what you do see here is a nice spike, strong spike of gamma rays, which peaks at around, roughly speaking, 100 keV band. And when you analyze the data more carefully, you find that it was, well, first of all, you see that it was delayed by about 2 seconds relative to the gravitational wave signal. Then you see that the spike was relatively narrow, even compared to the delay, about 3 times narrow. Delta T over T is about 1/3. And then when you analyze the data, you also find that it was followed by soft quasi-black body emission. It's hard, the data is not so great, it's hard to see it was exactly black body, but it was soft emission peaking around 20, with temperature about 20 keV, which followed immediately at 3-4 seconds. Okay. Then what we saw was a clear sign of relativistic ejecta. So in radio imaging, just you can see that there was something moving with Lorentz factor of 4 at late time of radio afterglow from that burst. So there is no question that it was relativistic jet produced by this event, as expected in the gamma ray burst context before. And there was this broadband synchron afterglow, radio, optical, X-ray, beautiful data, peaking as you see here, like at hundreds of days. So of course, many people, there's many hundreds of papers immediately jumped onto this data and simulated them, different models, I don't know, tens of models. But quickly, there was some convergence to basically this picture that what you see is a jet, which was narrow, with opening angle about 5 degrees. As we know from the gravitational wave data, the observer angle with respect to the axis of rotation of the merging binary was between 20 and 30 degrees. And so basically, during the afterglow phase, you see a narrow jet observed off axis. And from this modeling of synchrone broadband emission, people try to reconstruct the ambient density of, like, in the environment around this emerging binary and total energy of the jet, which is 10 to the 50 erg. Okay, and so it all came to this basic picture that we more or less understand what that was a decelerating jet that produced afterglow, scales of weeks to months to years. There was this massive cloud that produced what we call kilonova, macronova on time scale of days, and it picked an optical in infrared, and it was clear signature of radioactive elements being synthesized, our process in particular, in a massive cloud with a mass of about 5% of the solar mass, moving with, expanding with mild relativistic speed, few tenths of c, this heavy cloud. And so the real puzzle that remains is how gamma rays were produced, how this gamma ray burst was emitted. And I should mention that since I worked in this field for some years before this detection, so I remember very well how no one actually expected to see anything interesting in gamma rays. Well, I'm saying no one. Most people would tell you that that if you look at the gamma ray burst source off axis at 20, 30 degrees, you probably wouldn't expect to see gamma rays. Because this outflow, because as soon as you go outside the beaming angle of the jet, you expect slower material, and whatever you, the models that have been done, like hydrodynamic simulations of jet breakout, etc., you expect to see emission that was reprocessed to X-rays, maybe even soft X-ray, but not in gamma rays. And indeed, the burst that we see is strange compared to the other GRBs that we've seen before. So in this plot, you see many GRBs associated. These are short gamma ray bursts, classified as short duration, short height. This is the class that was associated for many years with neutron star mergers. And when we actually saw a neutron star merger, the burst that we see was off axis, but it was weak as expected, but was very hard. As you can see here, this GRB 1708, 17A is the counterpart of the gravitational wave event. It's 200 keV, roughly speaking. Well, if you extend the correlation of the observed GRB, it should be much, much softer. All right, and so people,
can I ask,
sure, go ahead.
this estimate of 20 degrees, whatever, off axis, is that coming from this, or the estimate of off axis was coming from something else?
From gravitational wave data. There was just by analyzing gravitation, how the two neutron stars merge and what kind of gravitational wave, the waveform that you receive, you can already estimate from gravitational data alone, you can estimate the observer angle with respect to the rotation axis. And it's about 20, 30 degrees. There is a significant uncertainty, but it's this kind of number, 20, 30 degrees.
Okay, thank you.
And that's consistent with the analysis of the afterglow, which came from jet, which initially, you see this jet with the delay for a simple reason. If I go back to the afterglow, my short discussion of afterglow, when you see a collimated jet, when you look at the collimated jet off axis, initially you don't see much because all the emission it produces is beamed within a narrow angle. But later, as the jet decelerates, this Doppler beaming becomes less efficient, and you start to see broader angle essentially, and then you begin to see the jet comes into the line of sight as a bright source. And that's what's observed there. Okay. So one idea which came up immediately is related to the shock breakout picture, which I will talk a little more in a few slides. But the basic idea goes back to, like, the basic picture of shock breakout goes back to 50s and 60s and 70s. So when you have a shock, and suppose in this case the merger itself somehow launched the shock, and that shock crosses the massive cloud that eventually meets the kilonova. As the shock comes to the edge of the cloud, where the density drops, it begins to accelerate. So shock dynamics responds to quick decrease, sudden decrease in density by accelerating. So its energy goes down as it goes to lower and lower densities, but energy per particle goes up. And as a result, the shock, so it's a self-similar solution that was obtained first by Sakurai in non-relativistic case in 1960. And you can find discussion in classic hydrodynamic textbook, for example, the Ablation right there. So that's a potential source of gamma rays in principle. So from this cloud, if there is a shock breakout, you could see something hot, which would potentially emit gamma rays. This idea, though, is in tension with, you find it quickly that it is in tension with data, because in its original form, let's say, because there are two constraints on this gamma ray source that come from the duration of the gamma ray bursts, which gives you this line. You can see my mouse, right, on the screen. So this line shows where you, basically it shows the minimum gamma that you require for any emission at radius r to arrive within 0.5 seconds. So high gamma is needed to compress, use Doppler compression to compress the duration of the burst within the observed window. On the other hand, high gamma is also needed to help the gamma rays escape, because if gamma is too low, then the emitting source becomes opaque to photons, just to scattering. And it's not self-consistent. So these two regions give you two, the shaded regions are excluded by these two constraints. And so you can see that the minimum gamma here is about 5. And when you compare it with the shock breakout problem, when shock comes to the edge of a mild relativistic cloud, in that simulation, you find that emission comes from when gamma is of Fourier unity, basically mild relativistic. So there is tension there. Okay.
Andrei, can I ask you a question about that? Like this tau t, like what are the assumptions that you plug in for the density at which that happens? Does it just come from the self-similar solution, or what do you assume there?
Yeah, so there is a numerical factor that reflects the, in the paper, which is published, you can see there are actually a couple of lines for the optical depth constraints, which have a numerical factor for a unity depending on how the density is stratified with radius. You're right. It varies by a factor of 2 or 3. But when you translate it to variation of gamma, it's very small. It's
okay.
Still, gamma 5 is the most conservative case.
Mm-hmm.
Actually, yeah. And of course, when you estimate the amount of mass that you have, you use the energy budget of the.
Mm-hmm.
Andrei, and you said there is a tension here. What is a tension exactly? I mean, you do have a lot of white space here.
A lot of white space, all with high gamma.
Yes, and so what's the problem?
And the problem is when you look at these papers that in particular apply to this burst and calculate at which point the shock should be emitting gamma rays. That is when it becomes transparent, right? When it comes to the photosphere. At this point, gamma is still like 1.5 or something. It's mild relativistic.
Okay.
Okay, but then you can ask question. I mean, okay, how do you know that the massive ejecta from neutron star merger, maybe there is fast ejecta? Why do they have to have this speed of like a few tenths mild relativistic speed that we see in the kilonova? And numerical simulation suggests that there is fast material. This is a snapshot from numerical simulations. And this white points show the mass elements that will later escape with high velocities. So you can see where they originate. A lot of them originate here at the interface of the colliding neutron stars. And you can analyze the distribution of the ejected mass of gamma beta for velocity. And then you still find that there's almost nothing above gamma beta for unity. Maybe it goes up to 2, certainly not to 5. However, I think these simulations have no hope because of their existing resolution to actually see the fast material that actually exists there and does move fast. And I will just describe why I think that there must be really fast, low mass, fast material ejected by the neutron star merger at the very beginning, basically. When the star touch and merge in milliseconds, they immediately eject low mass, ultra relativistic envelope. So one process, I will mention this briefly, and you can read in the paper if you're interested. One process is that is the ablation of neutron star surface by the neutrino emission that is generated at the interface of the colliding stars. So what happens there when the two stars touch, they launch a pair of shocks. They create this hot red sandwich with temperature about 20 MeV. And then this is a huge source of neutrinos. And so when these neutrinos propagate through the stellar material, some of them experience collisions. Neutrinos and antineutrinos collide with each other and turn into electron-positron pairs. So just zoom in on that red region. You see this blue material, which is the shock-heated material in the sandwich. You see the neutrino sphere here in red. And then from this neutrino sphere, you have neutrinos. You can calculate the flux of neutrinos, you know, the temperature of these neutrinos, and then you can calculate neutrino antineutrino annihilation rate, which works everywhere outside the neutrino sphere. So it works here, and it works actually even outside, above the neutron star surface. And this annihilation of neutrinos deposit energy in a clean form. They annihilate into electron-positron pairs. So when you look at energy per baryon, like in this region, somewhat below the surface, the energy deposit per baryon by neutrinos is not so high because there are lots of baryons. In this region near the surface, there are almost no baryons, but neutrino antineutrino annihilation rate is almost the same. So energy deposit per baryon is huge. And this neutrino front that goes ahead of the shock wave deposit the subphotospheric heating that has to ablate the neutron star surface. So we've done the calculation. It's essentially deposit heat, and there is a rarefaction wave, and that's how ablation works, right? We've done hydrodynamic calculation for that process, and this is the distribution of the ejected material, Lorentz factor of ejected mass. And mass counted from the outer edge. So little m is equal to 0 for the first, like, leading front of this ablating material. And as you go deeper, the Lorentz factor of this material decreases. So you can see this huge gamma beta starting from like 1,000, and it goes, you know, this like self-similar distribution of that. So what you create is a homologous envelope, ultra-relativistic envelope, ablated by neutrinos with total mass about 10 to the minus 7 solar mass.
Beta here is just V over C?
I'm sorry?
Is beta just V over C? So
yes, beta, oh, sorry. So beta is V over C, gamma is Lorentz factor associated with it. So gamma beta is full velocity, yeah.
Andrei, what sets this temperature of 20 MeV? Is it just a virial temperature for the shock, you said?
You know, the collision velocity up to 0.3 C, depending on the mass of how compact the neutron stars are. So they have tangential component, they have normal component, but anyway, so you know how much energy is dissipated in this collision per baryon, per nucleon, because you know the relative velocity of collision. And this energy basically is thermalized in first approximation. And that's how you find the temperature. Okay. So you know the energy density, you equate it to 8 to the 4th, you get a temperature. Or if you like, you just calculate energy per baryon. There are multiple ways of calculating it, radiatively efficient, radiatively inefficient regimes. In all cases, you find temperature between 15 and 20 MeV. Okay.
Andrei, I have two questions, if I may. So the first one is, I mean, is it 10 to the -7 what you would need? I mean, this would only come basically from the like interface where the two stars would touch. So this would be the order that you need for like the other numbers to fit, or do you need more? Or
what I need for the gamma ray burst?
Exactly.
Yes, that's the kind of number, but I will come back to this. The number of the envelope. So this is kind of first principle physics, if you like. I mean, estimate, still approximate, but I think that's what you should expect. 10 to the -7, and I'll look at it in a second. But okay, since you're asking this now, basically yes, this amount of material is very small. You cannot resolve it in existing numerical simulations. However, when you look at this envelope of 10 to the -7 solar mass, look at its optical depth, huge. And so as it expands with this speed of light, it basically hides whatever is happening at the center. You don't see because this envelope is opaque. It's also cold by adiabatic expansion. It becomes cold. It's dark and opaque. And its photosphere is expanding with the speed of light, and you don't see, and it grows. This photospheric radius grows with time, and you will see later. I will show that the GRB that we actually observe comes from the photosphere of radius about 10 to the 12 centimeters compared to the merger size, which is like 10 to the 6 centimeters. So it's a million times bigger. So basically, the effect of this very light dark envelope is to inflate the photosphere of the merger.
The second question I had was maybe a quicker one. Because you were saying this depends also, I mean, on the collision speed of the two stars. What would happen if, say, I have a very unequal mass merger, where basically I have more tidal disruption going on and less of a central collision? Would those numbers like still match, or would they go down?
Yeah. So if you have low mass stars, they would go down. Unequal stars, I didn't think much about that, but you're right. It is sensitive to the masses of neutron stars. The more compact they are, that is, the more massive they are, the bigger is the relative velocity at collision, right? Because they collide kind of much later when they're deeper in the gravitational potential. And you release more energy, more neutrinos, ablation is stronger. So this is like characteristic number. I took the default, like the fiducial model of people who simulated neutron star with mass 1.44 and equal mass, something like that. It could actually be slightly overestimated. It depends on the geometry, because here it is estimated like with isotropic picture, but of course this thing is not isotropic. Okay, but actually I like more this other way of inflating this envelope, which is robust and simple, and also gives a self-similar homologous envelope promptly, immediately after the merger. If following the merger of two neutron stars, you launch a shock into this massive cloud. That's the shock that we talked about before. But now, I think this shock that happens early, if you actually do the calculation, whatever internal shock crossing the cloud within the first second after the merger doesn't do much in terms of observation. It reaches the surface of the cloud, photosphere of the cloud, when it has radius about 10 to the 9, 10 to the 10 centimeters. It has some black body temperature, which is low, when you calculate the luminosity from this cloud, because of its small surface area, small radius, it's not a detectable source. So any early shock that crosses the cloud around the merger doesn't produce a GRB because it's too weak. It produces something, but it's not observable. On the other hand, it does two important things to that cloud. As the shock comes to this edge, it kicks the edge. It does this usual breakout business when it pushes the outer layers of the cloud to higher speeds. And in this way, it inflates an envelope with the extended profile of gamma beta for velocity of the same, qualitatively the same structure, that is the leading edge is the fastest and the trailing layers are slower. So that's one thing. And the other thing is that this shock loads the envelope, loads the ejected material with a large number of photons per baryon, about 10 to the 4, simply because it hits the material, and when you do the calculation, you find that it ejects about 10 to the 4 photons per baryon. This is the hydrodynamic simulation of the shock, early shock breakout. And you can see how it is distributed over mass. So again, little m is mass measured from the outer edge of the envelope. And so the fastest material is at m equal to 0 at the outer edge. And then the scaling here is m to the 1, approximately, just feed it the numerical results, m to the -1 quarter. You see it fits pretty well. Okay, and the total mass, in this case, it's certainly 10 to the -7. Even for gamma beta significant, it's a little more efficient and more robust mechanism for producing this envelope. So I like this one. To summarize, I think it's actually, one should expect, not only you need it from observations as I will argue, but one should expect inflation of a homologous, ultra-relativistic, dark, very light envelope around the merger remnant promptly, before anything else happens, before the GRB that we saw is emitted. Okay. And of course, you can calculate the density profile of that envelope, which is homologously, like impulsive ejection of mass with known velocity distribution. You find its density profile, how it evolves with time, it's self-similar. And you find in this lower box, you can see photon to baryon ratio, which is about 10 to the 4. Little m here is normalized to 26 grams. That's because, later we'll see, it's where the photosphere of that explosion is. It's the most interesting part of the envelope. This is the part that you actually observe when you look at it from outside. All right. So to summarize what's going on here, you have a neutron star merger at 10 microseconds. It does ablation. Then you have probably this internal shock. Especially, I don't want to go into details, but it might be, if you have questions actually about that, it's interesting to discuss also at some point, how two neutron stars merge, how we don't know whether the merger product is a massive neutron star or it quickly becomes, immediately becomes a black hole. But most likely when a plausible scenario when the two neutron stars merge, they last for a while because of rotation in a supermassive neutron star configuration. Then with some delay, they collapse. The remnant collapses into a black hole, which means that the object, the mass shrinks. Whatever magnetic fields it has in it also are amplified. And also you have now clean magnetic field lines because they go into the horizon of the black hole, and then you can launch the jet from the rotating spinning black hole through the Planck-Snag mechanism. So at that point you expect jet formation with some delay. And so what people argue that, okay, probably why we saw the GRB with the delay is that because it took some time for the jet to form, and it could be because it took some time for the neutron stars to form a black hole.
Andrei,
So, yeah?
before you move on, I just wanted to clarify one thing. So this merger and this expansion of the ablated material takes place in a vacuum, right? There is no like wind or anything that happened before? I mean,
from the binary before anything happened to before they touch. You mean? Yeah.
So this ejecta, this ablated ejecta, just expands freely in vacuum.
Yes, that's the picture. But of course, in reality, if you put an obstacle on it, to it, then you have to think about how the wind compares in density and Lorentz factor with your.
Yeah, but there is no obstacle, right? I mean, you are saying it's expanding in a vacuum because I mean, you started by saying that there is a shock breakout from something. So as if there was some kind of pre-existing envelope already. So
okay. So that's So not to confuse. So the picture is like this: you have two neutron stars. They merge initially. Let's say there's vacuum around them, nothing.
Yeah.
They ablate some material. Okay, ultra-relativistic, very little mass. It is followed on a time scale of seconds. Also, it's shown by hydrodynamical simulations by ejection of a lot of mass, like percent of solar mass, 5% of solar mass, that we will observe later as kilonova. Okay, so this material is mild relativistic, expanding with speed about 10 to the 10th centimeters per second, a few tenths of the speed of light. If at the early stages after you form that cloud, it is crossed by an internal shock from the merger. For example, you had the magnetar wind because this supermassive, still alive neutron star would act as a magnetar launching it. Magnetized wind maybe drove a shock, or maybe there was just shock coming from the merger itself. If a shock crosses this early, still small in size, massive cloud, as the shock comes to the surface of the cloud, it kicks its layers and inflates immediately ultra-relativistic envelope around it. Okay, so you create the structure roughly. This is what's pictured here. T equal to 1 second. You expect to generate a massive cloud. It's the kilonova, the dark blue. This is future kilonova stuff. Dense material, neutron rich, radioactive. Around it, you have inflated this ultra-relativistic envelope, where at the edge of this envelope, flow velocity diverges. Okay, so when you do the calculation, if you forget about opacity, suppose it's completely opaque, it just diverges. So you have a horizon. It's like when the jet is finally launched from the center, it expands now not in vacuum, not an external medium. It expands in a universe which has an unreachable horizon, running away with the speed of light. And the jet is ultra-relativistic. And of course, it will catch up first these deeper layers, which move slower with lower gamma. And as the time progresses, the jet will keep catching up faster and faster layers. But it has no chance, of course, to reach the first layer, which goes along with the gravitational waves. They go with exactly the speed of light, let's say. That's the basic picture. And then here behind this, you have this dark blue, which is the future kilonova.
Okay, but so light blue is your ablated stuff. Dark blue here is the kilonova stuff.
Dense stuff, yeah. So dark blue is 5% of solar mass, and light blue is 10 to the minus 7 solar mass.
Okay. Thanks.
Yeah.
And so this envelope is going to be very neutron poor, right? Because it's coming from the neutron star crust. I mean, that's not going to be.
It's a good question. It's yeah, there is nucleosynthesis. It's not radioactive material. It's not very efficient for our process, I think. I'm not sure how rich it is in terms of. So it does come from neutron stars, but the YE. The ratio of protons to baryons is regulated by neutrino emission and absorption. And so it is changed from what it was originally was. Of course, also it's completely decomposed at high temperatures into free nucleons. Then as the stuff expands and cools down, nucleons tend to recombine into helium. And then there are some leftover neutrons. So there are more neutrons than protons, but it's not really clear by how much. But you're right, there should be some neutrons also there. There's a neutron component, which which actually is an elephant in the room if you think of it. I wrote a few papers about this some years ago. The entire GRB theory is constructed as if there is no free different component in the jet, in the canonical GRB models. But in fact, there aren't free neutrons, and they do affect stuff. But it doesn't affect you still have the envelope, you still have the kilometer cloud, you still have the jet. The jet still has to drive a blast wave into the envelope. Okay. So when the jet comes to the photosphere, it will radiate a gamma ray burst. And you can calculate, let's say, if you meet 10 to the 46, if the energy of the blast wave 10 to the 46, 10 to the 47 erg, isotropic equivalent. Of course, it's much higher on the axis because the jet is collimated. So the blast wave that is launched by this jet, so it will drive a blast wave into the envelope. It will not have isotropic power because the jet is collimated. And how it is distributed over angle, we don't know. Actually, we're working 2D simulation, but I don't have an answer yet. Assuming that at 20 degrees, it has power which is like 3/4 of magnitude lower than on the axis, which seems plausible. And it seems like it's not finished, but hopefully it works out this way. You do produce GRB with the right properties, and that's the main message of my talk. I will try to explain now how you generate the gamma rays that you see by this blast wave. So the main point is that after you inflated this envelope and launch the jet, which drills through the massive cloud and then goes into the envelope, this jet breakout, it launches a blast wave that eventually is not seen because the envelope is opaque. But eventually this blast wave has to come to the photosphere and radiate. And the spectrum of that emission is a gamma ray spectrum that we observe, I think. One can also quickly estimate that white peaks at 100 keV, but let me just move on now because I think I'm a little slow. So let me just explain. Let me show first hydrodynamic simulation. So gamma beta, this flow velocity profile of the envelope. This is how it scales with this Lagrangian mass coordinate. Again, remember M is 0 at alpha H. This is stratified density. So if you launch a blast wave into this expanding envelope, that's what you will get. So let me jump here. So there's the material which is faster, right? That's the shock, the jump here that propagates through the envelope. And note that the jump remains approximately constant, shrinking slowly. Eventually, if you run it infinite time, it becomes almost nothing. But for many decades in mass, the jump remains almost the same. So if you introduce this chi parameter, which is the strength of the shock of the blast wave, is the ratio of the post-shock downstream gamma to the upstream. Just the jump of the Lorentz factor across the shock. It's about a factor of 2. Okay, and it stays at about a factor of 2. I can run again. It stays at about a factor of 2 through the range of mass. The photosphere is about here, it turns out.
So even though the material is moving out at essentially the speed of light, the shock is able to catch up with it.
Exactly. So the material is, so if you look at the state of the shock, let's say here, the shock has caught up with the material which has Lorentz factor about 3 at this point. And of course, it still has not reached even faster material, which is just next to it, okay, Lagrangian core. It will have to wait longer to catch up faster material and longer to even faster and longer. So it's racing toward the outer edge, but even if the shock, and it does move with almost speed of light, the layers ahead of it also move very fast. And the time it takes to catch up is is proportional to their relative, inversely proportional to their relative velocity, 1 minus beta. where beta is the upstream velocity that your target is trying to catch up. The closer beta is to unity, the longer it takes you to catch it up, to catch up with it. Okay. So it's also similar, right? It's just you launch a shock wave into this homologous expanding envelope. You know the properties of the envelope within a factor of a few, like its profile of gamma beta. You know, you have an idea of the energy of the blast wave, at least in your direction because you see it. And that's it. Here, the end of the problem formulation. You want to know the spectrum of the blast wave that emerges from that envelope. You don't have any free parameters really in this problem. You can calculate from first principles the dynamics of the blast wave and the emission of the blast wave. It's not easy, but I will show we've done it now. And the paper is unpublished yet, but it's submitted just a week ago. To summarize the theoretical properties with actual observed properties of this blast wave, it has one funny property that I wanted to highlight. The duration of the photospheric emergence of the blast wave at this photospheric radius r star. So star means photosphere here. So the delta T over T at the photosphere is basically the ratio of the Lorentz factors upstream and downstream. This is the jump square. The reason why is that because the observed time, it's how long it takes for the blast wave to catch up, scales as 1 over gamma squared. This radius divided by gamma squared divided by c little gamma squared. The duration, though, is set by the downstream Lorentz factor gamma. It's a hot shell which moves faster, and in the duration of it, Doppler compression corresponds to its own capital gamma, faster gamma. And so the ratio of delta T over T is just the ratio of the two Lorentz factors. So this model predicts that this ratio is a few, and the observed ratio is indeed 1/3. It's quite consistent. Then you can also calculate the Lorentz factor of the envelope layer, which will serve as a photosphere, and it's basically 3. It scales as 1 to the 8th. And when you apply that chi star, the ratio, you find the ratio is like square root of 3. You find that the capital gamma, the downstream, the source gamma is 5. Remarkable, of course, it's the same 5 that I told you before. So it's where the two lines, the two constraints, remember I showed the plot with constraint cross. That's exactly what the source should be, because what I'm talking about, the photospheric emission. Its duration lies in one line, and its opacity is 1, it was the other line. So of course, it's where they cross, it's exactly gamma is 5, and it does work out to 5. And you can calculate the energy that is produced by this blast wave. Then you know the strength, this factor of unity, times, you know, Lorentz factor of upstream material, times the mass. And the mass you also know, I told you, it's 10 to the 26. You can calculate it in this envelope. And you get a number which is consistent with the observed GRB energy. And finally, you can calculate the typical characteristic energy of the photons. And not surprising, the blast wave basically hits the existing photons in the envelope. And I mentioned before that you can estimate how many photons you expect, and it's 10 to the 4 photons per baryon. It translates to the energy per photon in this photospheric emission, about 100 keV, and that's what's observed. So to me, it was really convincing that I was excited about that. And so with Christopher Lundman, we've done now the full simulation that actually calculates the spectrum. I don't think I have time. So how much time is left for me to talk?
Well, we should probably try to leave 5 to 10 minutes at the end for questions. So if you could, you know, finish the talk in the next 5 to 10 minutes. 5 to 10 minutes, that's good. So I was planning to talk more about details of shock physics, but I'll go quickly and show the results of this first principle simulation that we have for the shock breakout. So I would like to emphasize that this blast wave is a shock wave, which is mediated by radiation. So there are different types of shocks. There are collisional shocks, like atmospheric explosion, collisionless,
plasma shocks, solar systems, supernova remnants, for example. Here we're talking about shocks which are originally launched in opaque medium, which is radiation-mediated shock. So this shock works like this. You have upstream. In the downstream, you reprocess the energy into radiation. Here, pressure is completely dominated by radiation. And so the upstream and the velocity profile of that shock is regulated by how radiation pushes back onto the upstream. It's like upstream comes to this radiation and sees it like a pillow, decelerating it smoothly, radially, by the radiation pressure. So the thickness of this transition in velocity is comparable to the photon free path for relativistic shocks. The plasma in these shocks, because they're so relatively broad, the photon free path, let's say the photosphere is comparable to the size of the system. Okay, so it's a really broad transition. The plasma stays completely in equilibrium with kinetic equilibrium with photons. So it has Compton temperature, about 10 keV everywhere. But the photon spectrum in this shock is not thermal because the photon bounce on this free path between upstream and downstream, and just like the Fermi acceleration, they gain energy. Okay, so plasma stays cold, but the radiation becomes not thermal. We developed a method to simulate it from first principles. Basically, it's MHD coupled to radiative transfer done with Monte Carlo. So we follow individual photons, many of them, like billions of photons. Tens of, it's not billions actually, no, so I take it back. 10 millions is enough. Yeah, I mean, unless you do simulations. This is the spectrum of radiation before the shock, we just some thermal loss radiation, black line. After the shock, we just heat up the photons far downstream, that's blue. And inside the shock, because of this Fermi process, Fermi-like process, you have no thermal spectrum. So when this shock comes to the photosphere, it will release something which is not quite thermal, okay? An interesting point here to make about the physics of such shocks is that photons that reach energies above MC square convert to pairs. Because we're talking about very energetic, high power shocks, and turns out the optical depth of photon-photon collisions is much greater than 1. So once photons come to the energy significantly above 1, they convert to electron-posting pairs. Now, as you see, there are not many photons in this region. Only a small fraction, like 1/1000th of the total photon number, will end up above MC squared. However, the number of photons is so big initially, like 10 to the 4 per baryon, that you have a potential of creating a lot of pairs per baryon. Okay, and your plasma becomes predominated, and your shock shrinks then. So in this simulation, actually, that I mentioned here is actually the number of photons per baryon was 10 to the 5. So the preloading factor was actually 100. And then you can see that the photon free path shrinks by a factor of 100, and the shock becomes much thinner because of that. There is a threshold for this phenomenon to work though, creation of pairs. Because when you look at how photons gain energy as they bounce between upstream and downstream of radiation-mediated shock, on average, in each bounce, they get energy of order of v squared over c squared. The v is the relative velocity of this converging motion, upstream and downstream. At the same time, the photons lose energy. Delta epsilon over epsilon, epsilon is the energy, photon energy units of MC squared, electron versus mass. Is a form of negative epsilon, recoil, Compton effect, right? So shock can Comptonize photons for non-relativistic shock only up to v squared over c squared, which is below unity, and therefore non-relativistic shocks don't produce pairs. Photons don't get above MC squared, but relativistic shocks do. And the threshold for pair creation is basically beta gamma of the shock should be above unity. We did many models. Christopher did many models. Christopher Luhmann verified it. Indeed, there's clear separation shocks that have relative speeds above, for velocity above unity, produce a lot of pairs. Okay, coming back to our merger, when you look at where it should be at this, in this parameter range, it's actually right here, actually a little bit below, it turns out, and it does not produce a lot of pairs. But nevertheless, we simulated it with complete Monte Carlo code, which does follow all pair creation events. And now also includes all the spherical expansion geometry. So basically, we follow the shock as it approaches the photosphere. And basically, you want to see what happens. As a physicist, you would like to ask, what happens to the shock when it comes to the photosphere? It should stop existing because the shock thickness is photon free path. But photon free path, by definition of the photosphere, exceeds size of the system when you cross photosphere. So radiation emitted shock is no longer supported. And so you want to understand where the energy goes. Okay, so it sits most in radiation, but I guess it tries to decouple from the plasma, and you want to understand what comes out. Like probably you will launch this velocity profile that used to be regulated by radiation pressure, now will steepen and form collision-less shock that you may expect. As an observer, you would like to ask the question, what is emitted? What emission you should see? And so you need to follow this transition to collision-less shock in order to be able to predict what kind of emission GRB this event should produce. The nice part of this problem is it's completely first principle problem. By the time when you look at what is emitted by this blast wave, you can forget about the merger, the envelope, you just have a photosphere. Well, actually, stratification of upstream Lorentz factor is important, but that's it. You launch a shock with given energy and you see what kind of spectrum it produces. So we've done this simulation, and you see here, so I have just a couple more slides to show the results. This plot shows energy density of radiation different times. 23 seconds is not observed, it's slab frame time, basically radius divided by c. The shock approaches 10 to the 12 centimeters, where optical depth drops to unity at about 30 seconds. So 23 seconds, the shock is still below the photosphere. Then at later time, it moves to lower masses, right? To the outward, in other words, masses counted from outside. And then, okay, radiation keeps moving, okay? So we don't see anything dramatic here, but when you look at the profile of gamma beta, that's how it transforms. That's the pre-photospheric shock, and it becomes broader and shallower, okay? And what you see here is the formation of a pair of two shocks. This is one collision-less shock, forward shock, and there is a reverse collision-less shock. So the mechanism of formation of pair of this shock, like this transition from radiation-mediated for two collision-less shocks, is actually straightforward. The plasma, the motion that used to be regulated by radiation pressure, suddenly feels that radiation pressure is not telling it too much, and it just continues to move ballistically. And the profile of velocity continues to steepen, and you form a caustic. So when you look at the density plot here, is the third panel, you see how what used to be one, that's the shock profile, the second snapshot. At the next snapshot, you see how density shoots up at the position of the caustic. So you have a very thin layer that keeps compressing until the density increases by more than 1,000. And at that point, the gas pressure now, not radiation pressure, gas pressure balances the run pressure in the shock. And at this point, it stops the compression, and you launch a pair of now collision-less plasma-mediated shocks, forward and reverse. Okay, that's the basic physics effect that works here. And it's really interesting, but then you can ask for that problem, how much energy you deposit into these collisionless shocks. And actually, it's something that we did not expect. But when you calculate this energy, you find it's almost nothing. It's like 1%. And so basically, the first approximation, what happens in this radiation-mediated shock breakout is that radiation peacefully decouples. Yeah, there is some leftover plasma motion, but it's mostly peacefully decouples. Photons just leak out, and whatever energy they've got, they deliver to the observer. That's it. Pair creation is not triggered. We see in our simulation there's some pair creation, but it's negligible. And to show the light curve, of course, it's a Monte Carlo simulation, so we see photons, what they do individually, and we collect them at infinity. That's the light curve from that explosion. And that's the spectral evolution. So the light curve has a delay, duration, and luminosity as expected. Delay is actually a little too big, but it's because we chose a delay, which is now rerunning it, make it a little short. It will not change anything except it will be at least 2 seconds. And this is the spectral evolution. So you start with very hard emission, and after a few seconds, it comes to basically a 10-20 keV spectrum is observed. So the bottom line is that this blast wave seems to give you the observed TRB just from first principles and within the accuracy of observation. And I guess I should stop now. Yeah. So this is like slide talking about future. The most interesting part I think here to do is to do 2-dimensional simulations and try to make predictions for future mergers. When you look at them at different angles, then you expect different luminosity, different Lorentz factor, different duration of the peak. If this mechanism is indeed at work for off-axis GRBs for neutron star mergers, that it's pretty much the same for all mergers except for the viewing angle. And you can make predictions for correlations between, let's say, luminosity and delta T over T, for example. It should increase with that, while luminosity should drop with that. And I'll stop at this point. I already did a little. Thank you.
Great, thank you. So we have time for a few more questions, and then people who want to go dive in further can join this afternoon's conversation. If you have a question, why don't you use the Zoom raise hand? So I'll try to make sure everybody gets their questions in. I guess a question I had was, are there, have there been any other, at least semi-viable proposals for explaining this this gamma ray burst? I mean, the story you told here seems pretty compelling, but what are the alternatives?
So what was discussed, so there are basically 2 existing proposals, to my knowledge. So one is shock breakout. This is what I discussed in detail. And I think that's the version of that process that works. Now, the other option is the emission from the jet itself, not from the blast wave that was launched in an envelope, but from the jet itself. That's similar to canonical GRBs that we observe on axis. And indeed, when you look at the same explosion on axis, you would see very collimated jet directed toward you, which would be so bright that completely overshine whatever side wave, blast wave you may think about off axis. And in that case, you would probably looking directly into the jet and some dissipative process that works inside this magnetized material in the jet. So in principle, you could tweak the jet model, but it's hard to do. Like, for example, if you say one proposal that was initially discussed and ruled out almost immediately is that you look at your gamma ray is the gamma ray burst is the gamma ray emission from off-axis narrow jet, and it turns out that it's peak position, spectrum peak, and luminosity are not consistent with that idea. Or you could imagine a jet which is kind of called structured jet, when Lorentz factor and luminosity, you can draw a function, try to adjust it so that produces the luminosity that you see. The problem with that, so it's hard to calculate from first principles, so you can try to, but in my mind, and actually it was always the problem known before the discovery of the burst, is that these sources are typically soft X-ray sources or hard X-ray, but no gamma ray sources. That's, yeah.
Good, thanks. Elias?
Right. I basically wanted to ask again about this 2D dependence, because if I remember like your comparison with the theory and the observations, you basically got something that was more like gamma is 3 versus gamma is 5. Like, do you think this is really just by, you know, the angle you look at this, or is this because, I mean, in your model, even this envelope should have some angular dependence, right? If you really think this comes just from, you know, this ablation, this would not be homogeneous. So what are your thoughts on that?
Yeah. I think the main factor is simply the power of the blast wave. The envelope is not exactly spherical symmetric for sure, but it should be quasi-spherical, at least at the range of angles of interest. But the blast wave is strongly anisotropic because the jet is so much collimated. And so basically, when you look at a small angle, there is more power. This capital gamma is higher, essentially. I mean, because you push with the piston is bigger. And when you go to lower theta, you come to this situation where this capital gamma is lower. And so you can draw a photosphere at different angles. The blast wave comes to the photosphere at different radii. And so that's how you can make predictions. You put a simple small spherical envelope, an anisotropic blast wave, and see how things depend on that. That's what we were trying to do. Hydrodynamically, it turns out, surprisingly, maybe, I don't know, it's kind of a nightmare of relativistic two-dimensional hydrodynamics. But hopefully it's solvable.
Okay, Roman, you get the last question.
So Andrei, it sounds like, I mean, what you're sort of proposing here is different from the canonical model for the production of GRBs. At least this is my impression. So then, I mean, so does it mean that this explosion was in some ways special? And if so, then why this physics that you describe here does not work in the regular GRBs?
So the key difference is the angle. So
yeah, but I mean, we do observe many GRBs. I mean, why don't we observe many GRBs which are slightly off axis and see these?
It's weak. That's right. Why? Because it's
so we just don't pay attention to it. We just say that this is not a real GRB. This is some noise of Luke and so on.
Yeah. So think of it: how many sources with luminosity 10 to the 47 erg per second, lasting a second, you would detect?
I have no idea. I mean, you're an expert.
Yeah. So it's hard to detect off axis. So when you look at in the sky and you collect gamma ray bursts from the sky, what you see are more distant, but really well collimated toward you bright sources, and they have different physics because you look right head-on into the jet. And I think for those sources as well, if you had a chance to look at the off-axis and you're close enough to detect it easily, this burst was marginally detected, but what distance was already 40 megaparsecs. So it's hard to detect from large distances. This is not a strong burst. But if you looked at them at 20 degrees, I think you should see something like that. In this picture, at least. You should see a sideway blast wave from the jet, which would propagate into the ejecta from the merger. And I think it is enshrouded with so similar dark envelope, and it will come to the photosphere and produce something.
So we should see this generically as we detect more neutron star mergers gravitationally.
Absolutely.
Yeah.
Hopefully, yeah.
Okay, well, thanks. Let's thank Andrei for a terrific talk. There was all sorts of fascinating stuff in there. And so thanks so much. And and those who want join again this afternoon. And thank you again for joining us and giving us that presentation.
The three same link, right?
Yes, same link.
All right. Okay.